Ik denk dat dat van u is, toch?
Dirk had dat voor mij meegegeven, maar dat moest terug naar hem.
Ah, het is voor Dirk terug te
Het is
geven.
voor Dirk terug te geven.
Dat was een... Ja,
Dat is al...
dat was stom.
Ja, dat is oké. Misschien is dat het beste. Test eens even uit. Moet ik iets opzetten? Dan staat daar op mute. Oké, misschien is dat alleen al gewerkt. Dus misschien... Hallo. Moet ik hier niks open doen? Ja? Ja, dat is... Ja. Dan jij... Ja, hallo, welkom. Yes. Ja. Oké. Deze wel? Ja, het zou handiger zijn als het hier ook... Maar, en deze werkt wel? Ja, ik weet niet. In de tussentijd kan ik al beginnen. Deze wel, maar de andere niet. Yeah, and these are the only mics that are available? Anna Fisher is not back yet. This works, right? You can hear me? Yeah. And we have two microphones. Okay, that's perfect. So, good afternoon, everyone. Welcome here in Leuven for the session From Leuven to Space in the framework of the Belgian Space Week. It's a big honor to have you all here, and in particular to welcome astronauts Frank de Winne, Anna Fisher, and also the VIPs of our university. We have with us here Rector Luc Sels, Dean Philippe Muchet. We have representatives of the city, Thomas van Oppens. So I will now give the floor first to Rector Luc Sels to welcome you here this afternoon.
Thank you so much, and a warm welcome to all of you in what we call the graduation hall of the university. This is actually the place where doctoral students usually defend their doctoral thesis, the PhD thesis, at the very end of their trajectory. And I'm on stage here almost every week, but each time I always go back to, I think it was late December 1989, when I stood here defending before my jury, who was sitting here behind me. So For the youngsters, the young talents among you, if you aspire an academic career or a research career, this is where you end, or at least where you have kind of an intermediate station before continuing in, of course, a higher level of expertise in academia, for example. Let me go back in history. The 24th of March this year marked exactly 30 years since the first time a Belgian went into space. Dirk Vriemhout then traveled with Space Shuttle Atlantis. And 10 years later, Frank de Winne, who is here today with us, followed in Dirk Vriemhout's footsteps. So we are also celebrating his 20 years this year. Frank is joined here today by Anna Lee Fisher. Mrs. Fisher, a warm welcome here in Leuven. It's a great honor to have you here on this very special occasion. Thank you for also taking the time to share your insights and your thoughts with all the people present here today. So 30 years of Belgians in space, critics might say that our small country is a latecomer in space, but I see it differently. That we were already there as a small country back in 1992, I think is just a sign or a symbol of our perseverance and our determination to play a decisive role in the exploration of space and in revealing its secrets. Because research in astronomy, in physics, in mathematics, in engineering, related to space research has been here for a much longer time than the previous 30 years, of course. We have a very strong capacity in those domains. I was then, in 1992, doing my PhD in sociology at this university, far away from astronomy. So I was more concerned with how people interact with space here on Earth. Nevertheless, also for me, Dirk Vriemhout's story strengthened my faith in what science can do for humanity. And even today, their testimonies of former astronauts, for example, are of very great importance in explaining to young talents and to us all what role Belgian science can play in the space industry and in space research. But the influence goes wider, of course. For many young people, the journey of these iconic personalities strengthens the feeling that they can build careers in science and make a difference in pushing boundaries, pushing frontiers. In the scientific community too, to be honest and open with you, we sometimes need heroes to reinforce our courage and our perseverance, and to convince young people and young researchers that through a scientific education and a choice of a career in research, they can help solve the great challenges facing humanity. The big questions might be out there in space. The need for solutions is particularly urgent here on Earth, and the two are interrelated, of course. Today, to end my remarks, you are here at KU Leuven, as I already mentioned, in the graduation hall of the University Hall, in a very special hall that we only use for very important guests. I'm referring not only to Frank de Winne and Anna Fisher, but to all of you. Thank you for being here. KU Leuven is, as you can see, a very old institution, a very old university. We will celebrate our 600th anniversary in 3 years, 600, so we were founded in 1425. And if you go back in time, Erasmus Collegium Trilingue, the maps of Mercator, the Big Bang Theory, actually a discovery by Lemaitre, they all emerged here in walking distance, springing forth from a conscious mind with a willingness, a curious mind, apologies, with a willingness to challenge how we see the world. We continue to do so today. KU Leuven is a leading university in today's Europe, top 3, 4, 5 within the EU, if you look at research performance, and with a very, very strong position in the domains that really are crucially important to the topics that we will discuss this afternoon. But today it's not about KU Leuven, it is about how our science contributes to the study of space and the view of Earth from space. Especially in our science, engineering, and technology group, there's a lot of research capacity and teaching with great relevance to space and space research. But this is also true in the other two scientific groups, especially in the social sciences and humanities, and to some extent also in the biomedical sciences. We will be happy to give you a taste of that in a moment. I wish you a splendid afternoon and a lot of inspiration for the rest of your life and career. Thank you.
Thank you. Thank you very much, Rector Luxels. Then now I would like to give the word to the representative of the city, Thomas van Oppens.
Good afternoon, everyone. Good afternoon. Good afternoon, Mr. Rector, future space explorers, dear and beloved astronauts. I'll keep it short because I know you're not here to listen to me. You're here to listen to a beloved national monument and a prime example for future space explorers. So I will keep it short, but I want to talk to you about something that happened here 100 years ago. 100 years ago, we didn't know as much about space as we do today. And back then, Einstein thought of a formula on how things moved in space, and he realized that if his formula was correct, that space must be growing bigger and bigger all the time. And he thought, this cannot be right. So he added something to the formula to stop space from going bigger. And it got spread all over the world, but someone here, not far from here, and I mean like literally down the street here, he looked at this and he said, no, this is right. Space is constantly expanding, and it all started with a Big Bang. It was thought of here, right here at this university, in this very street. And so, why I'm telling you this is that because space exploration is very important. Space is constantly expanding, and it is everything that we are doing today has some kind of link to space. We are talking with astronauts today, which is very lovely, but when you think about your future, and when I thought about my future, when I was very young, I thought, I want to be an astronaut too. I really thought that. I really thought I want to be an astronaut too, but I was 6. And then I learned about your adventures, and then I realized I don't want to be in space that long. Like a year or 100 days? I mean, that's too long. I don't want to be away that long. And so I decided I want to be an astronomer, which is also a pet. And later on, I thought I want to be an engineer. I want to design satellites, and so on and so on. Eventually, I became an economist. That's a different story. But the point is that there is so much to do in space. And I hope that you, maybe after this afternoon, you will see a future for yourself here in Leuven, to think about how we can solve space, how maybe we can think about better laws when we talk about the trash that's floating around space, and we can prevent that with different countries together. How do we go about when one country says, yeah, I want a base on the moon? Is it allowed? Can every country do that? Who owns the moon? Who owns Mars? Etc., etc. There are so many questions to be asked, and I want you to think about that, not only this afternoon, but also maybe in your future academic career. And maybe, and I hope so, that will be in Leuven. Thank you very much.
Thank you. Thanks a lot, Thomas. So these were the words of welcome. Welcome to you all. Also welcome in name of ESERO Belgium. ESERO is the school program of the European Space Agency. And it is actually led here from Leuven by KU Leuven, but it's a national program, so we have partners all over the country, and some of them are present here today as well. We have a packed program for today, so we will start, we have had the welcome, the intro. We will follow this with an astronaut session, because we have 2 prominent astronauts here, one ESA, one NASA astronaut today. They will briefly introduce themselves, and then we have time for questions. Then we will follow that by a session on space research and development, because as was pointed out by the 2 introductions, space is really important for us on our own planet as well. And so that's something we want to show as well. And we also want to show you the wonders of space with a session on what if we look up in the sky. Then, since most of you are in school or are students, we also have a session on space and education, because space is a great way to teach STEM in school, and so we'll have a few short talks about that. And then there will be closing words by our dean, and we'll invite you to the reception. If you registered for that, you're very welcome to join. So we'll start with the astronaut session, but first of all, why are we doing this here today? Well, this week is the Belgian Space Week, and this Belgian Space Week in 2022 was actually an initiative taken by Viscount Dirk Vliemhout and Viscount Frank de Winne to commemorate the birthdays of their first space flights. For Dirk Vliemhout, our first Belgian astronaut, this happened 30 years ago in March 92. Yes, I'm correct, right? And then for Frank, it happened 20 years ago in October 2002. So I think this deserves an applause, because this is a birthday of the first flights into space of our two Belgian role models. And now, what is next, actually? Why are we having this Space Week? Because we also want these role models to inspire a next generation of explorers, and you might be part of this. And it doesn't have to mean that you will fly into space. It can also mean that you, in some way, are triggered by the beauty of space, or that you contribute in some way to safeguarding our own planet by using space data. And you will see how this is happening right now, and this is only going to increase in the future. So now I would like to give the floor to our two astronauts. We will start with Viscount Frank de Winne. And Frank, I'll give you the mic. You're welcome to speak about how you got to become an astronaut. And I have some slides here, so I can give some figures with the slides if you want.
Thank you very much, Catherine. Very warm welcome as well from my side. Thank you very much all for being here. It's a real pleasure and an honor to be here in this not old university. It's an old university, but especially a beautiful university, and especially a university that is thriving and is adding to finding the solutions that we need for solving all the problems of the world, as the director was saying here. Because indeed, we look into space, to the future, we look into what we can do, but we also have a lot of issues to solve here in the world, and the two are indeed very closely connected. I was not looking to a Belgian astronaut to have a role model to become an astronaut when I was 6. That did not exist at that time. But I grew up in the time that there was the series Star Trek on television. So I'm a very big fan of Star Trek. Yeah? You can find actually pictures of me in a Star Trek uniform, and I sometimes go to Star Trek conventions. And I shared this with Samantha Cristoforetti, by the way, who is also a very big Star Trek fan that just came back a couple of days ago from space. So I've always wanted to sit in the big chair of Captain Kirk and say, warp 9, engage. Yeah? We are not there yet, but okay, maybe with some talent, eventually we will get there. So I decided, since there were no astronauts flying in space at that moment in Europe, I was very interested by engineering, so I decided to start an engineering career. And I was also very interested in astronomy, because at that time there were the big discoveries of black holes, wormholes, time travel through wormholes. All this was discussed in popular magazines, so I was very fascinated with that. But since flying was also something that I wanted to do, I also joined the military academy and I became a pilot. And later on I became a test pilot, joining both the engineering part of my endeavors of what I wanted to do, and then the flying that I wanted to do. And I was lucky enough that in 1989, I saw an advert in the Standard, one of our newspapers, of course, here in Belgium, in Flanders, that said, European agency is looking for astronauts. And said, maybe I will apply. And that's where it all started. I applied to this advert, and eventually became an astronaut in the European Space Agency, and indeed was very privileged to be able to fly in 2002 a 10-day mission to the space station. And then in 2009, a 6-month-long mission to the International Space Station, which was, of course, very interesting because we were already then preparing the future. Because, yes, we don't stop with the International Space Station. The ISS today is where most of our astronauts fly. It's our bread and butter. It's really the working machine today where we do a lot of science, biology science, material science, science on human physiology. There is almost no domain in science that you can find that we are not trying to advance the scientific goals or knowledge that we have in society. But we don't want to stop there. Anna flew with the space shuttle some time ago, about 25 years ago, is that correct? Yeah, 84, so it's even more than 25 years ago. But she did her career also after that in NASA, like I'm now doing my career in ESA, and she actually worked on the Orion spacecraft, which is a spacecraft that is sitting on the launch pad right now to bring humans back to the moon. And we will not stop there, we will also go to Mars. Yeah? And the question is, why do we need to do that? Why do we need to invest? We are presenting a program to our Minister Council in 1 month where ESA also wants to go to the moon. We are actually presenting a program that would allow the first European astronaut not to fly to the ISS, but to actually walk on the moon. And so why should we do that? Why should we invest into that? Because we know that these endeavors, first of all, they inspire young people like you. We have heard it, a number of testimonies already, to invest into STEM careers, into science, technology, engineering, and math. And yes, we have very big problems here on Earth. Think about climate change. But we will not solve climate change solely by changing our behavior. Yes, we need to drive less with the car. Yes, we need to eat less meat. I'm all in favor of that. But that alone will not solve the problems. We also need technical solutions. We need engineering solutions. And that's why we need to invest into STEM and where we need a lot of young people like you investing in those careers. And the inspiration that space can bring helps with that. The second part is innovation. Yeah? We need to solve a lot of problems when we go to the moon. On the moon there is no oil, there is no gas. We will have to have a completely green energy system if we want ever to have a long duration moon base. We will have to recycle everything that we bring to the moon. So the circular economy in the moon has to be a reality. It's not just a word, it's not just something that we can do for 80% or for 90%. We will have to have a circular economy for 100% on the moon. And that's of course very much linked to what we need to solve here on Earth. And this innovation of course creates jobs, creates employment, creates people that can work in industry and do interesting job. And I think we will have some people this afternoon talking to you about that, how this has inspired them and how they are now contributing to space exploration. The third thing is international cooperation. It's clear that, yes, the world today is not in a very good state. I don't think that I need to draw a lot of pictures with that. But nevertheless, think about it. Our ISS is a small bubble where we are still able and willing to work together. Just 3 weeks ago, a Russian female cosmonaut launched from a launch pad in Florida on an American vehicle. And 2 weeks ago, an American astronaut launched on a Russian vehicle to space from Baikonur. Despite all the difficulties that we have, we are still capable of having one small item where we can still talk and work together. And I hope that we can use this as an example where we can expand and where we can hopefully bring this to a better humanity. So international cooperation is the third driver. And finally, of course, we discussed about it, we are here in a university, it's science. When we explore, when we will go to the moon, when we will go to Mars, we will bring a lot of new knowledge, a lot of scientific discoveries towards society. And we have seen in the past, starting with the Big Bang 100 years ago, here in the university, that this knowledge is actually what we apply today, what is helping our lives today. And so that's why we explore space, and that's why I'm really grateful that I can share my experience with you here today. Thank you very much.
Thank you very much. Then, now I would like to give the floor to the first mother in space, Dr. Anna Lee Fisher.
Thank you so much,
I
Katrina.
have slides here, so if you see something that's interesting, you can just go there.
Okay.
And at the end, there's the M&M video.
Oh, do you think the older audience would be interested in that? Okay. Oh, I'm so happy to be here with you today in Leuven on this last day of Space Week. It's been a very, very busy week, but I've really had a wonderful time getting to explore the different cities and to be able to see and talk with folks here about the things they're interested in. My career path to becoming an astronaut was a little bit different than Frank's. When I was growing up, they didn't even have any astronauts. It was all science fiction. And then the first astronauts that were selected in the United States were all male, all test pilots. And women in the United States were not even allowed to join the military and fly high-performance aircraft and go to test pilot school. That didn't happen until actually much later, even after the first women were selected for the space program. And so, but when I was very young, I always loved math, I always loved science. I was incredibly shy, a nerd, one of those people who loves doing their math homework. And it didn't occur to me that I would have the opportunity to become an astronaut. But when I was even in second grade, I was the first person in my family to go to the university. And I remember when I was in second grade, at that age, I realized very early that education was the key to everything, and that anyone who's willing to work hard can get a good education. My father was in the military, and we moved so frequently that when I was 13 in 8th grade, I had been to 13 different schools. So basically we moved once a year up until when my father retired from the military. So anyway, but I always loved math, I always loved science, and we were stationed at Fort Campbell, Kentucky in the United States. And because Alan Shepard's flight was a little delayed, when we got to school, our teacher, we crowded around her with a little transistor radio. Most of you probably don't even know what that is. We didn't have iPhones and things like that back then. But I listened to Alan Shepard, the first American to go into space. And as he was talking to Mission Control, for some reason that captured my imagination. And it was everything I would want to do, combining my love of math and science with space exploration. And I listened to him, and as he talked with Mission Control, I decided right then and there that that's what I wanted to do someday if I ever got the opportunity. As I went on, I was very fortunate that when my dad retired, I got to do my high school education in one place. As I said, I was the first person to get to go to the university, and I went to UCLA and started out in chemistry. And by this time, I was starting to think, well, maybe I'm not going to get to have that opportunity to go into space. But I was trying to figure out what I wanted to do exactly if that wasn't going to be a possibility. And I decided I wanted to combine my love of math and science with going to medical school and becoming a doctor. And in the back of my mind, I still said, well, maybe I'll get to be a doctor on a space station someday if I don't actually get to be an astronaut. So I was very busy in the middle of my medical training, and I don't know if any of you have doctors in your families, but the medical training in the United States is pretty grueling, and I hardly had a chance to listen to the news, read newspapers or anything. But one day I was having lunch with one of my fellow medical school students, and he happened to tell me that NASA was looking for astronauts, and not only pilot astronauts, but mission specialists. I quickly looked over the form and saw that I had all the requirements to apply for the job I had always dreamed about. And back then, it took quite a while to get that together. There was no internet. So you had to, call and get an application sent, fill it out, and it was a month before the deadline, and it took me almost that entire month to get all of the information that they required. And so I got it in about a day before the deadline, and then 6 weeks later, found myself in Houston interviewing with the first group of women that had ever been interviewed, and 6 months later, found myself to be fortunate enough to be selected in that first class of astronauts for the space shuttle. There were 35 of us, 15 pilots, 20 mission specialists, biggest class NASA had ever selected, and definitely the most diverse, and the first 6 women. That was, I still, even today when I think back on that, I have to pinch myself because it was the thing that I wanted most. We then started our, initial training, and I finally, after a couple of years of doing various jobs in the office and a lot of training, was called into my boss's office when I was about 8.5 months pregnant, and he said he wanted to assign me to a flight, and I have to admit I was pretty surprised. I felt that I was going to get a flight, but I didn't know that it was going to come when I was pregnant, and I said, sure enough, definitely send me in, coach. And so I had Kristen on a Friday morning, and a Friday morning, and then a Monday morning. We have an 8 o'clock meeting every Monday, which continues to this day. And I wanted to be there just so that all my friends and colleagues knew that although I had just had a baby, I really was going to honor my commitment, both to NASA and to myself for my dream. I also said I was the first mom to fly in space, and my daughter always tells me that I owe it all to her. So, as daughters will do. That was a really amazing year, doing the 2 things I love most. It was a very exciting mission. For the first time in history, we were going to go into space and bring back these 2 very large satellites that were deployed from an earlier shuttle mission, and the rocket engine that was supposed to take it from the low Earth orbit that the shuttle was in up to geosynchronous orbit, where communication satellites are, failed about 4 seconds into what should have been a 4-minute burn. And we were given the task to figure out how, along with many, many engineers, how to go and bring these satellites back, because nobody had ever done that before. The really big drivers for the mission were the insurance underwriters, who wanted to recover some of the millions of dollars that they had lost. So that year was just so fun, challenging, trying to figure out how you were going to actually handle these huge satellites. I was the robotic arm operator on my flight, and we had to figure out a whole process, and I'm not going to talk to you about all that today, but just to say that it was just one of the most amazing times of my life. And then after we got back from our flight, I was assigned to my second flight, and then I was about 6 weeks from my second flight when the Challenger accident happened, and of course that impacted all of us. Did a lot of work on that, decided that we wanted to have our second child, and I learned that having 2 was a lot more work than 1. And I wound up not planning it, but taking a 7-year leave of absence. And after that, I wanted to go back to NASA. And when I came back in 1996, it was probably the hardest thing I've ever done in my life. So for any of you that ever, want to do something different for a short period of time, or a longer period of time, like in my case, coming back was really difficult. And it was like coming back to a whole new world, because all my classmates had pretty much left and gone on to other positions, and so there were a lot of new people. There was also this thing that they gave everybody when I showed up, a computer. It may surprise you, but when we first were in the office, not everybody had a computer. And we did business by having meetings and sending memos. We didn't have email. So I came back, and that first year was like I said, a whole new world. But then it put me in a position, because I had taken time off, that I was the only person around that remembered what it was like in the early days of the shuttle program, and that everything wasn't always operating as smoothly as it was at that time. And so they put me in charge of the space station branch of the astronaut office, which meant that I got to work with all the international partners, primarily the Russians at that time, but still all of our partners. And it was just an amazing experience to try to get all these countries to work together. You'd be amazed at how passionate people are about the standards for their procedures, for example. And I had to try to figure out a way to incorporate what the United States wanted, but also what the Russians, Europeans, and Japanese, and learning about all of our differences. And that time was almost as much fun and as challenging as going into space. And so over the years, we developed many important partnerships. And so I'm particularly saddened, as Frank was mentioning, about the problems we've been having now in Ukraine. But I am so proud that those relationships that we built in those early days and continued over the years is so strong that it's even able to stay working, even though the politicians at the top do not get along. So I did that for several years, and then I was assigned to work on the Orion vehicle, which working on the displays. And, it's been kind of interesting with a background in chemistry and as a medical doctor. Here I'm doing things like helping to design the displays on the new Orion vehicle. And I just think, and then I retired in 2017. Although I don't say I'm retired anymore because I've had the privilege of doing many different things, but in particular, the U.S. State Department asked me to go around and speak to young people all over the world. And it's just so wonderful to go to countries that don't even have space programs and to see the children's eyes light up when an astronaut comes there to spend some time with them in countries all over the world, Romania, Moldova, Brazil, Cyprus. And everywhere I go, you see that enthusiasm and that excitement. And not everybody wants to be an astronaut, but everybody, I think, is interested in space. And you are all very fortunate, or those of you that are going to go on and become teachers, you have a critical role in taking that passion that I see in them and making them believe in themselves. I always like to tell folks, again, I had that dream when I was very young and never thought it was possible. And you just do not know what is going to happen in the future. And you should have a good education and be prepared for opportunities when they arise. And so I'm really excited about where we are in the space program now. We have the commercial crew program with Elon Musk and Jeff Bezos and launching to the International Space Station. And so after all these years, we're able to launch from the United States. And then the United States is working on going beyond low Earth orbit. Hopefully, we're going to go back to the moon and start to not just go to the moon, which in the 1960s, just doing that was difficult. That should not be all that difficult anymore with all the new technology we have, but to actually go to the moon and build bases and learn how to live on the moon and another body outside of our own planet, so that we will be ready, hopefully, to go to Mars, hopefully in the future. Maybe someone in this room might be a part of that first crew to go to Mars. And anyway, I've really been very privileged, and it's been an honor to be able to be one of the first women that went into space for the United States. But I didn't do that, as Frank kind of said, to be a role model. I was just following my dream of what I wanted to do. And being the first mother in space or being a role model just came with the territory. I was really just passionate about what I wanted to do. And anyway, I just wanted to say I really hope you all find that same kind of passion and have as wonderful an experience. And perhaps some of you can go into space and follow in the tradition of Crystal McAuliffe and teach students from space. And I want to just thank you for your time today, and we'll be happy, I guess, to answer questions. Thank you so much.
Thank you very much. Actually, now we start with the Q&A session. You were so kind to also submit questions when you registered for the event, so I'm going to go to the questions. As you see, we have also very nice images of, actually, you could just explain what's happening here. This is fascinating.
Oh, this is a video I use usually when I'm talking to little kids because they enjoy it, but I've found that adults enjoy it as well. It just gives you a little idea of what it's like to be weightless. It's really so much fun. There's so many neat things that you get to do, but our commander would reward us by giving us candy afterwards. Not as good as Belgian candy, but there's really fun ways that you get to eat things when you're weightless, and so it's just a lot of fun. So we can. This is a video that goes on through our entry and stuff, so you can just kind of watch it as we're talking of questions.
Thank you. Yes. So we have some submitted questions, and we'll start with the first one. I think it can be answered by both of you. The question is, what is the hardest part about astronauts training? And it was both submitted by Lab Onderwijs. Are you here? The person who submitted that question, and HDC Leuven. Are you here? Yes. Okay. Hi. Thank you for the question. So, for each of you, what was the hardest part of the astronaut training?
I'll go ahead and take that first. Physically, the hardest part of astronaut training is working in that large white spacesuit, the spacesuit that you go out from the shuttle into space and do a spacewalk. You put on that suit that's 4.7 psi, and then you get in the water and they put weights around you to make you neutrally buoyant. But physically, that's the most difficult. But to me, the really hardest part is just all the information that you need to know. For the shuttle, there was a lot that you needed to know. For the space station, even more so. And so that, to me, the most difficult part was there's just a huge amount of material that you needed to learn in order to be a good crew person.
I hope it works, that one. Apologies.
Yeah, so the space station training is a little bit different, of course. I fully share what Anna is saying. Physically, the EVA training, as we call it, for spacewalks is definitely the most challenging that is there on a physical side. But on a personal side, for me, I'm an engineer, I'm a pilot, a little bit of a scientist, but I'm very bad in languages. I failed French and English when I was in high school. I had to do the second time exams, in August or something like that. And then I went to the military, had to study French to become an officer, imagine that. And then I became a pilot. Okay, we need to speak English as pilots. And then as an astronaut for the space station, I needed to learn Russian at the age of 40. This was for me definitely the biggest challenge. And I was literally studying every evening from 8 till 10 Russian language for the first 4 months of my training. Because of course you got lessons during the day, but then you got a lot of homework for the night. The second difficult part for me was the travel. Well, if you train for a space shuttle mission, all the training was in NASA, it was in Houston. ISS training, the people that train now, they train in all the different sites because the US part of the NASA part of the training is happening in JSC, the European part in Cologne, the Japanese part in Tokyo and Tsukuba, the Russian part in Star City. So I was traveling for about 2.5 years around the world, living basically out of a suitcase for 2.5 years, being away from the family. And that was definitely a very hard part of the training as well.
Mm-hmm. Thank you very much.
I would just add one little thing, just being one of the first women in the U.S. space program made me, it didn't make the training harder, but you knew that some part of your brain that people were watching, and some people didn't think women should be doing that. So that just added a little bit in the back of your mind that whenever you did something very difficult, that you really wanted to be successful. So like when we went to water survival training, there were reporters everywhere taking pictures of everything that you did. So I'm really very happy that the 6 of us all completed our training and all flew in space. space. So that added, I wouldn't say that it was a huge thing, but it did add something that you always had in the back of your mind.
Thank you. Next question from Gijs Goderis. Is Gijs hier? Hallo Gijs. Jij vroeg, you asked, do you have specific working hours and how much free time do you have?
As an astronaut, normally your day, and I'm speaking now on the ground, it tends to be a sort of a normal day. When we were having our initial training, you would work somewhere like around 7:30 perhaps to 5:30, but it depended a lot on what your particular job was. For some jobs, if you were a Capcom in mission control, for instance, talking to the crews on orbit, you might be working the orbit 3 shift, which is when the crew is asleep, and it's usually in the middle of the night. So you had a very varied schedule frequently. But to me, after completing medical training, where sometimes I was up as much as 36 hours with no sleep whatsoever, coming to NASA was actually, no matter how hard I worked, if I worked 12 hours or 20 hours, it always seemed easy in comparison to the kind of hours I had in astronaut training. In terms of what it was like in space, for the shuttle missions, they were so heavily scheduled because really every minute on orbit is precious. And so we were scheduled for 16 hours a day, and then 8 hours of sleep. So NASA at least thought you needed some sleep when you were doing a very difficult job. We really didn't get a lot of free time because, again, my flight was 8 days. The longest shuttle mission was 14 days. I think if you were longer than a week, they gave you a day or half a day off. But there's always things that you have to be doing to take care of the vehicle. But so we really didn't get time off when we were on orbit, except for the 8 hours of sleep. But it's very different for the space station.
Yeah, thank you, Anna. Indeed. This is a regime that you can do, like Anna said, for 8 days or 14 days at the most, and even then they had a kind of a small break. But you cannot expect, of course, people for 6 months in a row to be busy, scheduled every single day for 16 hours. It's just not sustainable as a human being. So in the space station, we have more or less a regime like we have here on the ground. We are scheduled 12 hours a day. We start at 7:30 in the morning with the morning DPC, daily planning conference, and we end in the evening with an evening DPC. Of course, before that, you need to prepare your own food. You need to have breakfast. After that, you need to have dinner. Nobody is preparing anything for you. You have to do everything yourself. But then the Saturday and the Sunday are kind of more relaxed days. Although relaxed, the Saturday morning is the cleaning day in the space station. We don't have men that come up to just clean our space station, and certainly not women. That would be certainly bad. But we have to do it ourselves, so that is the Saturday morning. The Saturday afternoon, we usually pick up the things that we could not finish during the week. There are always tasks that you have overrun or that you were not able to accomplish, and we try to do those on the Saturday afternoon so that at least all the work for the week was done. And then the Sunday is indeed more a relaxing day where you are usually scheduled not to do any task except exercise. We do exercise every week. And the Sunday as well, we have our weekly family conference, it's called, where you have the ability to talk with your family with video for about an hour. Yeah, and that is then scheduled for all the crew members separately. And then the Sunday evening it starts again, because the Sunday evening around 6 o'clock you have again your planning conference to prepare for the week that is to come. So yes, you have some time off on the space station, but it's still a very scheduled regime, of course.
Thank you.
I would just add that several of my friends that flew on board the space station made a comment to me that I found very interesting, because we have an electronic timeline that the crews on board station follow, and all the activities are color-coded, whether it's a maintenance or whether it's science in a particular area. So when you look at your schedule in the morning, it's very colorful, all the different colors for the different activities you're going to do. And there's a red line that indicates the current moment. and then you watch that, they said you watch that red line move across the schedule, and you're supposed to, you can gray out the activity that you've completed. So by the end of the day, you're hopefully going to just see all those colors grayed out. And, and they talked about the pressure it put on you they said there was like following the red line, and then you're not doing that for just a week or 2 weeks. You're doing that for 6 months, or in Scott Kelly's case, for a year. And even though you get time off, I think it's, from listening to their stories, it's a pretty tiring experience. I think the shuttle is more like a sprint, and station is more like a marathon.
Thank you very much. The next question from Carol Urlings. Are you in the room? Well, the question by Carol was, what is the most unexpected challenge that you faced during your mission? It's 2 questions actually, but let's answer the first one first.
The most challenging that I had was, of course, something that was totally unexpected as usual. I was scheduled to repair, or not to repair, to take out an electronic box of our Melfi freezer. We have a freezer on board. Now actually there are 3 freezers on board that freeze samples up to -80 degrees. Because the astronauts, we are not the scientists, of course. We are operators, we are executors. We get procedures, we do blood draws on ourselves, we do urine collection and so on. And then we freeze all those samples in a freezer at -80 degrees, so they can be brought down back to the ground for scientists here in the university, because I took certain samples for the KU Leuven, for example, that then the scientists can examine them here on the ground. And so one of those electronic boxes in our Melfi freezer was broken, and it had to be repaired. Now in space station, when you're in microgravity, you cannot cool computers like this one here, yeah? Here the computer gets hot, and of course there is a small fan inside, and then the hot air moves up, and you get cool air inside, and then it cools down. In space station there is no gravity, so this does not work. So a lot of our computers are put on what we call cold plates. So it's a plate where there is cold water circulating in the plate, and the computer is put on top of it so it can get cooled and it doesn't overheat. So when I had to replace that computer, of course, I had to disconnect the cold plate. So I disconnected the first connector of the water outlet going out, and then I disconnected the second connector, which was actually the inlet that went out. And when I disconnected that connector, the water just came spraying out at high pressure, because this water is, of course, circulated at high pressure by the pressure pumps. How does this happen? Well, somehow a command should have been sent from the ground to close the valve upstream. Somehow either this command did not go through or it was missed. Okay, there were debriefings afterwards, of course, but that valve was not closed. Secondly, those connectors are usually what we call quick disconnects. There is a small ball in the connector itself, so if the water flows, this ball goes against it and closes it automatically. This quick disconnect did also not work. So failures usually are one after the other. So then I'm there with this hose with really a lot of water spraying out at high pressure. And you have to understand the space station is operated at 110 volts DC, not AC, DC. Now, water and electricity does usually not go very well together, and certainly not DC. And of course the water floats around. It's not like it's just going to the floor and then the outlets. No, there is electricity everywhere and the water is going everywhere. So the only thing I could do is quickly, I first tried to reconnect, but it didn't work. The pressure was too high. So I took the hose, I put it under my t-shirt, so at least I could contain the water. I yelled for help. That was a second good decision that I made. One of my crewmates came quickly down and disconnected the whole rack, because there is the water supply goes through the rack. He disconnected that, and that of course stopped the water supply, and then I was hanging there in a whole bubble of water around me. Then some other crewmates came up and they came with towels. They tried to catch all the water that I didn't catch under my t-shirt, and then we dried up everything, and so we were still in a safe place. But that was quite of a surprising moment, I must say. For me, it's the only time that I took a shower in the space station in 6 months. But the ground afterwards asked, did you swallow any of the water? And I remember that, of course, the water was everywhere, and of course I got some inside, but I say, if I now say yes, there will be investigation, because that water is not very good to drink. So I said, no, everything is okay. And then we hang up the towels, and the towels in the space station, they get dried out over time, and then the water is recycled. And the next day we looked at those towels, and they were all brown. Really, because of course the chemicals started reacting with the air and whatever. And I was thinking, should I say something or not? Finally I didn't, and I'm still alive, so I'm okay. So that was the most, I would say, unexpected challenge that at least happened during my space mission.
That's really funny. Yeah, just a side, it wasn't me, but I was Capcomming in Mission Control, and Don Pettit, I think you maybe know him, and he called down one morning, and they have a hot water dispenser, that they use for coffee in the morning, and usually the crew would never call down before the morning DPC conference where they tag up. And he told me that the hot water wasn't working, but he had fixed it. He took it apart and had put in, I think he flew coconut oil on board. And he said, and I used coconut oil for the seals. And I was thinking to myself, oh, please, why did you say that? Because just like you said, the whole back rooms, everybody had to go do all these studies about how coconut oil would. But it was a real emergency because they needed their coffee in the morning. I'm sure you understand. The most challenging thing that we encountered on our flight, we were very fortunate. We had a very packed number of days, and everything went just as we had trained, with one exception. And so in the middle of the first spacewalk, when we were going to retrieve the satellites, and it's kind of hard to describe all this, but there was a piece of hardware that went over the top of the satellite. And I was supposed to release from the point where I had grabbed it, and where they were holding it in the payload bay, put this new piece of hardware across the top that had a special grapple fixture. The arm is designed, you can't just go grab anything. The thing you're going to grab has to have a special grapple fixture on it that the arm is designed to fly up to and grab it. And at the time, we did not have continuous coverage with the ground. And our crewmate Dale Gardner said, it doesn't fit, and it's not going to fit. There was an interference of some sort. That's one of the things you worry most about when the satellites were on orbit, so we weren't able to fit check all the hardware just to make sure there were no problems. And that was the one area that we were concerned before we launched. And we had spoken with our flight director and said, if there's any problem that comes along where we can't do everything with the arm, we would like to be able to go to our plan B, which is to actually hold the satellite by hand instead of having to grab it by the arm. And nobody had ever done that before. So we had a quick conference. Dale explained to us the problem. We understood that there was no way we were going to make that piece of hardware fix. And so then when we came up AOS, when we regained communication with the ground, we told the flight director what the problem was, and we asked permission to go to our backup plan. 5 minutes they took to give us the go. And as you know, later on in the space program, after Challenger and so forth, I doubt that would have ever happened. They probably would have said, come back in, we're going to go have a meeting, we're going to go study this and go over to the water tank. And so we went to our backup plan, which was something no one had ever done before. And, we weren't even sure we could do it, where Joe had to hold the satellite by hand. And you have to realize if you're holding a big satellite like that, you can't see anything. So we had to tell him, how to maneuver it, pitch it up, And so anyway, it worked. And we successfully got the first satellite in the payload bay. But to this day, I'm always amazed that Mission Control had that confidence in us and gave us the permission to go ahead and do what we knew that we had to do. And I think NASA became a lot more risk averse later in the missions, and I doubt they would have done that later on. And that was it. Everything else went well.
Thank you very much. We'll move on to the next one. Actually, this is for you again, Anna. What was your greatest challenge being a female astronaut?
You know, I always tell folks that when we got selected as astronauts, I felt like a surfer who caught a wave at just the right moment when societal norms were starting to change. You know, the Mercury 13, the women that tried to get in as Mercury astronauts and were told in no uncertain terms to go away, they just weren't in the right place at the right time. And the 6 of us were. And so that was just that one challenge, but it wasn't a challenge really to us, but a challenge to our management. I think the hardest challenge for me was working in the spacesuit. As I said, that's physically the most difficult thing we do. When we were selected, we didn't even have a shuttle suit. So I had to use the Apollo A7LB suit that you see them walking in, which each of the Apollo astronauts had their own suits fitted specifically for them. Pete Conrad was the shortest of the Apollo astronauts, so they adjusted it as best they could for me, but it was still a very poor fit. And doing a spacewalk in a suit that fits you is difficult. Doing one in a spacesuit that doesn't fit you is even harder. And you're one of the first women doing it, and everybody is watching everything that you're doing. So that was really the hardest thing physically and mentally. We actually tried to get a spacesuit small enough to fit the smaller women in the office, and we really weren't successful because the shuttle suit is a 2-piece suit with a hard upper torso and a lower torso. And to get that upper torso small enough to fit the smaller women, you could barely get into it. And the DCM, the display module across the front, is the same size, whether you're an extra large or an extra small. So you had a lot less useful arms. And everything you do in space on a spacewalk is your arms and your hands. And so the really best EVA crew members are the ones that have orangutan long arms. Will do the best. So that was the hardest thing and the biggest disappointment, that we were never able to get a suit small enough. So maybe some of you in here who are good engineers could help work on that problem.
It's a call for action. Thank you.
Yeah, and it's a problem that has not gone away. I was just in the debrief from Samantha's mission. As you know, she came back, and they asked the question, what was the hardest thing in your flight? And she said exactly the same thing, the EVA, because the Russians have only one size of suit for everybody. And so, of course, they can adjust it a little bit, but also for her, it was very difficult to work in a suit that was actually too big for her. And so it's very challenging. As Anna said, an EVA is very challenging if you have something that fits your body very well. Doing it when it doesn't fit is twice the work.
So what they finally decided to do for the shuttle program is you had to fit into a medium or a large. I think they may have eventually got a few smalls, but definitely not the extra small. And for example, in the fact, there were, I forget who it was that was going to, I think it was Anne McLean, went out to do a spacewalk, and she was in the medium suit, and she used the medium for all of her training. And then when she actually got out on her first spacewalk, she felt it was too large, and so she changed her mind, even on orbit, and they had to adjust a suit a little bit smaller so that because you want to be really tight in those suits. On one hand, you want them really tight. On the other hand, you want them easy to get into, and it's a real challenge.
Thank you. So we are going to take one last question. Yes, I think this is a nice one. In what way has your perspective on the world changed since you were in space?
You know, when you look at the Earth from space, it is just amazing. You don't see any borders. You just see this one beautiful jewel against the vast blackness of space. And you really do start to feel more like you're from planet Earth than the respective country that you come from. And from listening to my colleagues like Frank, I think even the longer you are in space, perhaps the stronger that feeling becomes. I don't know that my perspective changed anything, because I've always thought we lived on a beautiful planet. When little kids ask me, what's your favorite planet? Well, I go, obviously Earth. And it's just, it just makes you, it just brings home the message even stronger that this is a planet that is, for any of our lifetime, the only one we're going to have, and that we really need to take better care of it and also each other. I know I'm trivializing history here, but when you look at an area like the Middle East, or now you look at Ukraine or any of these areas, it just makes you sad, because you know, you only get a short time on this planet. My grandmother lived to be 105, which is, you know, really long for humans. And it just makes you sad that we can't all learn to get along better and take care of each other, because it really is truly amazing. And I'm hopeful that now, as more and more people will have the chance to go into space with SpaceX and Boeing and Jeff Bezos and Blue Origin, because I think as more people see the world from that perspective, perhaps maybe we'll start changing people's attitudes a little bit, and we'll do a better job in the future, hopefully.
Thank you.
Yeah, thanks, and I can only subscribe to that. So one thing is, of course, this very tiny atmosphere, the thin atmosphere that you can really see from space, that it's really, really tiny, really gives you the impression how small this planet is in this immense universe, yeah? And how vulnerable or fragile that we are, and that we need to take care of it. But certainly in today's world, and I said this already in the speeches before, there are no borders. Huh? We are just one planet. Borders are imaginary lines that human beings one day have drawn on a map somewhere. Yeah, but they don't exist. You fly over Europe, there is no border between Belgium, Germany, Poland, Ukraine, Russia. It just does not exist. Yeah, and yet we are fighting over those imaginary lines that we have drawn some time ago on the map. So I hope indeed that one day we can all get inspired by human spaceflight, by people testifying about that, and that we can get a better world.
Thank you very much. So we would like to thank you for being here with us today with a souvenir from Leuven. This is for you and for you. Thank you very much. I'm sure that people in the audience have more questions, but I suggest we first move on with the program, and then if we have some time left, we can take more questions, okay? So, thank you very much. Now, let's go to... Now it's time for the prominent guests to sit back and relax. You can just see what is happening here in Leuven, how KU Leuven also contributes to space research, because we are landing in this session now. And so we'll have very brief talks, between 8 minutes, 5 minutes on different topics. So we'll talk about what, when you look up in space, what are we finding there now? But what if we look down on Earth as well? What can we learn about our Earth, our climate? How about the laws of space? Because as you know, satellites are being sent to space, just think of Starlink, etc. But can we actually do that? So we'll have a session on, or a brief talk on space law. Then Marie Beekman, who's an engineer, will talk about her path to work in the space industry. And then Oksana will talk about how she uses space for archaeology. So we'll start off this session with Denis, who will talk about the space research. This is for you. You can introduce yourself.
Yeah. So good afternoon, everyone. So my name is Denis Defrère. I work here at KU Leuven, where I teach exoplanet science. And I will give you a brief introduction of some exciting projects we are working on here in Leuven. And I'll start with this picture of the James Webb Space Telescope. This is the most advanced telescope that has been ever built by humanity. It was launched more or less 1 year ago. And we have contributed to this instrument here in Leuven. We have worked on the development of one of the instruments, which is called MIRI, and we are also participating in the science case of this instrument. It was designed to study really the origin of the universe. So this is the first picture that was released of the James Webb Space Telescope. It was in July this year, announced with President Biden. And what you can see here is really astonishing. This is a deep field image of the universe. All these points that you see here are galaxies. They contain 100 to 200 billion stars each, and they are really, really far away, from 4 to 10 billion light years away. And it's a really tiny, tiny patch of sky. So if you take a grain of sand in your hand, you hold it like this, and you look at the size of the grain of sand. This is the size that you see here. This is the size of this patch of sky. So it's a tiny size, and we have James Webb sees all these beautiful galaxies in this tiny patch of sky. So we are working on the scientific exploitation of the James Webb Space Telescope. I show here a few images from this year, actually. So on the left side, you see a beautiful image of dust shells around a binary star. It's really the first time we see this kind of phenomenon around. We can image this phenomenon. You see on the right, the top right, you can see dust in a disk forming exoplanets. So we are studying what kind of mechanism are taking place right now to explain this disk shape. And then at the bottom right, you can see an image of a distant planetary system. So the dot that you see are real planets in different colors. And so here in Leuven, we are developing models to understand what kind of planets are in this image, the size, temperature, what kind of chemical composition they are. So we are working on many instrumental projects here in Leuven. You have an overview here of this project. I won't go into detail for all of them. I will mention on the right side, you can see Mercator. Mercator is our own telescope that we operate. It's located in La Palma on the Canary Islands. And so we use that for research, but also for education. In the middle, you can see a project under development, like the Marvel array. So it's a 4 telescope that will be linked together to detect and characterize exoplanets. And then on the left part, on the right part for you, it's an exciting project we are working on for the long term, like the LIFE project. It's for beyond 2040. The goal is to detect life on exoplanets. Also the Einstein telescope. This is a major project to build a gravitational wave detector here, we hope, here in Belgium. In 10 years from now or 15 years from now. I will go quickly on this project. It's called the ELT. It's the Extremely Large Telescope. It's a 40-meter class mirror in size, and it's currently being built in Chile. I was there 1 month ago. It's really amazing, and you can see compared to the atomium, it's really, really big. This will revolutionize many fields of astrophysics, and we are really hoping for this telescope to be online. And we are working on here in Leuven. We are working on one of the instruments for METIS, for DLT. It's called METIS. It's a spectroimager, and I show here one of the possible future image that we could obtain with this kind of telescope. This is the Alpha Centauri system. So this is the closest star to us. You can see on the right part, this is, you see the sun, and then you see the Alpha Centauri system. It's a binary, it's even a triple system. 2 of the stars are really like the sun, similar to the sun. And with this instrument, METIS, we can image the planetary system around this star. And what you see on the left is a simulation assuming that there is a Venus planet and an Earth planet around Alpha Centauri. We would be able to see them and to study them with the METIS instrument. So this is really the goal of exoplanet science right now, is to detect planets similar to Earth. Another project that we are working on with different faculties here in Leuven is the Einstein Telescope. It's an underground facility, really a state-of-the-art, world-class facility to study gravitational waves, and it's really to study high-energy phenomena in the universe, like the collision of black holes or neutron stars. So I will end with a few links. If you want to learn more, I'll put a few links about the Institute of Astronomy here in Leuven, the Institute of Theoretical Studies, and also the link to the masters that we have here. We have 2 masters, and you will hear a little bit more about that later. Thank you.
Thank you very much, Denis. Then we'll now move on to the next speaker, that is Gabrielle Delannoy. And instead of looking out, we'll look down.
Good afternoon, everyone. So I'm a professor here at KU Leuven, but before I came to KU Leuven, I actually worked for a long time at NASA. I'm not an astronaut, though. So my field is water management, hydrology, and I teach Earth observation. So looking from space to Earth. When we look from space to Earth, we see the atmosphere, we see clouds, we see aerosols. If we take away that atmosphere, we see ocean, ice sheets, and we see land. Land with some moisture, vegetation, and snow that all of you know. Why do we see it? Well, it's because light from the sun is actually hitting our land surface. The land surface is reflecting that radiation. It travels through the atmosphere, and the sensor captures the light. But the light that we see with our eyes is not the only type of radiation that's around us. There are much shorter wavelengths, and there are much longer wavelengths. So the shorter ones are, for example, blocked by the atmosphere, gamma or X-rays. But then the visible light is let through. So there's a window in the atmosphere where visible light is let through. Then we get the longer wavelengths, infrared, which tell us something about the temperature of the Earth. And then there's more radiation blocked just for our own safety. And then there's microwaves, long wavelengths, which are not harmful, that are naturally emitted by the Earth, travel through the atmosphere, and can be received by satellites. So for Earth observation, we will have sensors in those 3 windows in the atmosphere. So visible, infrared, and microwave. What we see, the temperature of the land, and then typically moisture in land. That's what we measure with microwaves. So in 3 windows we measure, and we have 2 types of satellites. We have those satellites that just peacefully travel over the Earth and see what's happening, so they passively collect the data. And then we have the satellites that beam, or they send pulses themselves. That radiation is interacting with the Earth, and then we check out the reflected radiation to see what's happening on Earth. So that interaction with the Earth is always the thing that we want to measure in space. So we measure then snow, for example, vegetation, soil moisture, or soil temperature. So Earth observation started a while ago with photography taken in hot air balloons. Then we started to develop aircraft, and with the World Wars, we got into microwave remote sensing. It's only by 1957 that the first satellite was launched, and since then, there has been an exponential growth in satellites. There are currently more than 5,000 satellites operational and orbiting around our Earth. There's another 5,000 just around there. I am not a big fan of these large numbers, not at all, but that's a different debate. What I am a fan of is that the increase or the advances in technology have helped us to have now an unprecedented view of our Earth. We see much more variables, we see snow, soil moisture, all these variables that help us. And I'll give you a few examples of topics that we work on in our department. The first one is soil moisture. At a very small scale, we need moisture in the soil to get food on the table for agriculture, right? So that's local applications. We also want moisture in peatlands, so that carbon is actually held in the soil and that it's not expanded into the atmosphere. We also want to know soil moisture to predict where fires would be likely or less likely. For weather forecasting, we need to know the soil moisture, flood, drought forecasting. All these applications, we typically tackle them with microwave remote sensing. Microwave remote sensing sees the upper layer of the soil, and then via some calculations, we are able to estimate what's happening in deeper layers. So that's microwave. There's one special satellite that doesn't use electromagnetic radiation, it uses gravity, and that's the GRACE mission. It's just the pull of the Earth that tells us where there's a lot of water and where there's less water. But it's very coarse scale data. Yeah, so that's one application, soil moisture. Vegetation is another topic. If you look from space, you see green as vegetation, right? And then now and then you see some logging or degradation happening. But those forests, they live and they grow again and it becomes green again. And then it's very hard to see how vegetation is actually affected by human impacts. So we try to detect or find new methods to see what's actually happening to our forests and other ecosystems. A new application is snow. There's currently no satellite in space that is dedicated to measuring the amount of water in snow. So it doesn't exist, even though many people rely on snow water for drinking water, for irrigation, for hydropower, for energy. But despite that shortage of not having a satellite, we actually decided to look into existing satellites and see if we couldn't, by any chance, tease out some information. And we managed. Here at KU Leuven, even though we are not an alpine country, we actually figured out that we could use Sentinel-1 to measure the snow depth in mountainous areas. And that's an example here. Sentinel-1 can also be used for other applications. This is Antarctica. If you look good, that ice sheet is changing in time all the time. But here there's a glacier moving, and by its velocity, it's actually ripping the ice sheet apart and it's breaking down. So that's very important to monitor climate change, changes in water availability. Finally, we work with a lot of data, a lot of different satellite data, but they also have limitations, right? So they perhaps only see a surface layer, like the visible or the microwave data that I was talking about. They don't go deep. There are gaps in time because the satellite is not there all the time. So what do? We also have models. And models, they summarize all the knowledge we have about our Earth, physical processes. We will combine the models with all the data that we have available via what we call data assimilation. And this way, we obtain the best image or picture of our Earth. We also call this a digital twin, something that we can work with and do science with. So these are some applications for Earth observation. Thank you very much. If you have any questions, feel free to ask.
Thank you very much. Thank you, Gabriella. I suggest that we keep the questions until the end of this session. Okay, so we'll first have all the talks, and then if you have some questions on this session, you can ask them. Thank you, Denis, Gabrielle. We'll move on to the next speaker, that is Philippe Deman, who will talk about space law.
Hello, good afternoon, everybody. Hope you're ready to hear about the exciting world of space law after hearing boring stories of actual astronauts and people working in STEM sciences. My job is to make this a little bit more attractive, I guess. I'll also tell you a little bit about what we're doing in terms of space law here at the university. If you have been following the news a bit recently, and actually the past couple of years, and have been looking at what is going on in space and what is in store for us in the future, and the plans of various spacefaring actors, you might be forgiven for thinking that there's not really a lot of rules in space, because apparently countries and companies can basically do anything they want. Just a little bit less than a month ago, we had the massively successful DART mission by NASA, which gave an answer to the age-old question, what happens if we fly and crash a really, really expensive spacecraft into a rock far away from Earth? The answer is it moves a little bit. which is an important answer to get. Then there is obviously other less important missions. We have billionaires flying their cars into space just to remind us that they have a second company producing cars. We have billionaires competing with each other to see who can fly the most satellites into space in the shortest period of time. We have companies that think, well, we've exhausted Earth and we now need to move on to the moon and asteroids and mine them. We have obviously other companies saying, well, maybe we want to spend a little bit of time in Earth orbit and feel a little bit like astronauts, and they offer opportunities for space tourism. There's plans by companies, but also by countries like the Arab Emirates, who want to build a colony on other planets like Mars. This is an artist rendering, obviously, for a plan to have a colony on Mars by 2117, so just wait a little bit. But we also have more recent, let's say, examples of activities that some people question whether they should actually be allowed, yes or no. For example, ASAT tests, countries launching missiles into their own satellites simply to show that they can. So if you're asking yourself, are there actually any rules in space? I don't blame you for asking the question. The answer is yes, there are, and there have been since the dawn of the space age, or at least the very first, let's say, activities in space sparked a lot of questions about the legal aspects. What can we actually do and what can't we do? When the former Soviet Union launched their first Sputnik satellites, a lot of questions arose. Countries were asking themselves, can they simply fly their satellites over my territory? Don't they have to ask for permission? Does the Soviet Union now own that orbit in which they fly their satellite? What if they have a nuclear weapon on board of that satellite and place it over my territory? It's kind of scary. So a lot of important questions, and it's not unreasonable to ask them because this is the time of the Cold War, a time of huge international tension, not unlike we are experiencing today. So when you say Cold War, a lot of people immediately say space race. So the space race, obviously a race between the former Soviet Union and the US to see who can fly dogs into space and what happens to these dogs when they are into space. But also more important questions like what happens if one country lands on the moon before I do? Can they simply claim the territory for their own? In order to give an answer to these questions, states do what they do best, which is sit around a table and talk for a really long time, which ultimately resulted in the signing of a massively influential document, which is what you see here on the screen, the Outer Space Treaty of 1966, entered into force in 1967. That's the full space treaty. It's not just a part of it. It's just 2 pages, a couple of articles that basically laid down the foundation of everything we're still doing to this day in space. Yes, we have other treaties, we have national space legislations, but ultimately everything still boils down to this one document that was adopted about 55 years ago. It gives, even though it's very short, a lot of answers to the questions that states had at the time, which is, can the US claim the moon as its territory? Of course not. We cannot appropriate space, which is something that this document provided. Can we actually, or do we have to give permission for other states to sense from space, remotely sense our territory? No, because that's covered by the freedom to use and explore outer space, which every single state has. Every state has the same freedom to use and explore outer space, which also means you have to take into account the interests of other states. You can't simply use space in a way that makes it impossible for others to use. So all of these rules are contained in this one single document. The biggest challenge now is to continue to apply this important treaty in a way that takes care and addresses all the challenges that these new activities that I mentioned at the start, which they all raise. Obviously, some of these challenges are not new. These have existed since the dawn of the space age, but they have been exacerbated, they have increased in importance simply because we're no longer talking about a couple of countries launching a couple of satellites. We're talking about many more countries, including private actors as well, that launch not hundreds but thousands of satellites in the next coming years. The problem is sometimes a little bit less expected. For example, you may remember the reports of astronomers being very upset about the light being reflected by the Starlink satellites at the beginning. So light pollution is something that we have to address, but more importantly is another source of pollution, which is that of space junk or space debris. If we have so many more satellites in space circling very crowded orbits, we need to have appropriate space traffic management and tracking capabilities to make sure that these don't collide with each other, because once these start colliding with each other, it might very well be difficult to contain these collisions, and we might end up with low Earth orbit or other important orbits that simply are impossible or no longer fit for use by states and by future generations. A specifically important challenge here is to avoid as much as possible extending Earth warfare into space. We see many countries these days increasingly saying that they think war is inevitable in space, that we should prepare for war in space, and we have to be dominant in space to avoid others from gaining an advantage there. And all of these things basically present what we call the 3S challenge to space: space safety, space security, and space sustainability. And it's these three challenges that space law basically tries to address. And if we saw initially the space race in the 1950s, 1960s inspired countries to sit together and to adopt space treaties for the first time, we are seeing that this new space race involving private actors and a lot of more countries is also inspiring countries to come back and to discuss space legislation, both at the national level and at the international level. At the University of Leuven, we're contributing in our own way to these projects and to these new legislative initiatives. We have, at the Center for Global Governance Studies, where I work, we have been awarded over the past couple of years 2 of the 3 main EU research projects on space traffic management, and we have been working on that together with universities across Europe, of course. We have a couple of research or doctoral research students studying specifically these issues of space sustainability, space debris, and military uses of space. Personally, I have been involved as a member of the Belgian delegation to the Committee on the Peaceful Uses of Outer Space of the United Nations, and have been fortunate enough to put the item of space mining basically on the agenda of the United Nations as well. So we're seeing now a lot of development in that respect as well, and we're contributing in our own way to that. There's also a military, let's say, manual that we have drafted together with the University of McGill in Montreal, Canada, that tries to give guidelines to states on how to apply international law to military uses of space, because there's still a lot of uncertainty about that as well. There's a lot of things that we hope you can contribute here as well. I know we're trying to get you into sciences and math and engineering, but also maybe consider space law as a possible future subject. We have a Master of Space Studies, which I am sure we will discuss in the next session on space and education. If you already want to know a little bit more about that, there's a QR code. It's not just space law, don't worry, it's also space sciences and technology, and quite unique in that respect, because it combines all of those things. I think that's what I wanted to say, so.
Thank you very much, Philippe. So yeah, keep in mind, if you have any questions at the end of this session, we have a few minutes for questions, okay? Then we'll now move on to the next speaker, Marie Beekman, who will talk about her path to space industry.
Hello, everybody. So my name is Marie Beekman, and I'm obviously very happy to be here. And I will be presenting you my path to the space industry. Oh yes, I'm already giving it away. So this is my path. It's not filled in yet. First of all, I'm not this kind of person who was like wanting to work in the space industry my whole life. I actually had no clue that this was possible. I was really fascinated about how things work. That was really my thing. Like, I wanted to know everything about everything, literally. I would be this person who would be receiving a birthday card, you know, the ones that you open up and they play this annoying song. I would be the one to rip it open and to find out, how does this work? Yes, so that's kind of where it all started off, me and my birthday card. And obviously, or not maybe super obviously, but I decided to go for industrial engineering because I hoped that that was going to help me find out how everything works. And it kind of did. But then there was one special night. So this was my engineering part. And there was one special night where I was at a regular student party. Maybe a bit drunk, but okay. And I was actually meeting a guy and we were just talking, and he told me at one point that he was studying aerospace engineering at TU Delft. What? At TU Delft? That's in the Netherlands. That is very close by. This was amazing. Like really, I was like, okay, so you can actually learn how satellites and rockets work here close by? Wow, so I kind of left the party immediately. I went home behind my computer and I looked it up. It was kind of too late for me, or I felt so, because I was already in my master's, already almost graduating. So I was like, damn it, I'm not gonna start all over at TU Delft. It was very, very cool what they're doing actually. The program is really amazing, but that was a bit too much. And I stumbled into this Masters of Space program here, the space studies here in Leuven. And I was so excited, really, you have to check out the program. We had classes by Frank de Winne himself. So this is the part where I became a real space nerd, and I saw that it was possible. And we had classes by Frank de Winne. This was so cool. The stories that he tells, his vision on everything, it just inspired me even more. But also the space law classes. I am the industrial engineer space nerd. But how cool is it that there are actually laws and that the booklet is very small, so you can learn very quickly on what the laws are actually. But how they apply it and all of these things. Also like a course on biology was taught. This was so cool. How does the body behave? So before this class on the biology, I still wanted to go to space maybe, but then I was thought, what happens to your body when you are up there? I'm not so sure. I think I will stay down with my satellites. So having class by Frank was not the only thing we did. We also got to know a lot of companies, of which one of them is actually Kinetic. And when I got to know this company, I learned that they were actually building the full satellite. So a lot of companies are building a piece or building a software or building a part of it. And they are actually building the full satellite. That was it. I was sold. Then one day I heard a talk by Stan Ilsen, and he told me about his job as an operations engineer, which again, I had no idea existed. And that was when it really, really happened. That was it. I wanted to be an operations engineer at Kinetic, for sure. So I applied, and as it so happened, they were actually looking for an industrial engineer, me. And I got the job, and right now I am working every day in the clean room. You can see me here with my funny suit on. This is me every day in the clean room working on these two babies that you can see. The mission that we are making is called Proba 3. We will launch in 1 year, maybe 2 years. We'll see how fast I can get it done. But I am really, really loving my job, and I never expected that I would get here. So actually, maybe what I want to say to you now, I want to talk about your path to the space industry. And I just want to tell you that there are so many companies out there. Like, it's crazy once you get to know how many space companies are actually out there. And they're not only looking for engineers, they are looking for a crazy amount of stuff, like all the jobs that exist. Actually, the space world is also looking for all these people. You know, we also have a cleaning lady. She actually comes into the clean room and she cleans around the satellites. This is so cool. And so I guess I want to wish you good luck, but I am sure that my good luck is not going to get you anywhere. It will be more your passion and your enthusiasm. That is so, so, so important in this world. When I'm doing recruiting myself now, I will always take the person who is enthusiastic, who is showing that his passion is really to do this, whatever job you want to do. So that's really my takeaway message for you guys. Thank you very much.
Very inspiring. Thank you, Marie. So, I hope, is anyone already considering a career in space? Please raise your hand. Yes. Super, yes. I see some hands raised. Well, and even if you're not building a satellite or thinking about what can we shoot into space, you can still become an archaeologist and also use space. And I'd like Oksana Burnayeva to come and talk about how she uses space for archaeology.
Thank you. Okay, good afternoon. So my name is Oksana Burnayeva and I'm an archaeologist, and I actually needed space in my research. So archaeology is the study of the human past using material remains, basically. But today archaeology is so much more than that. For example, digital archaeologists, they use digitization, analysis, and visualization of large data sets generated by field research and museum collections. And geoarchaeologists use methods from earth sciences and remote sensing techniques, such as LiDAR, magnetometry, ground-penetrating radar for the geological survey. Okay, yeah, we are witnessing how humanity is discovering space at an incredible speed. Now, we have the unique opportunity to observe our own planet from space using satellites for environmental monitoring, meteorology, cartography, and so much more. And archaeologists use remote sensing to monitor grave robberies, to identify ancient settlement areas, and so much more. In my book, Reconstruction of Physical Activities of Two Central European Migration Period Populations Based on Interstellar Changes and Aerospace Imagery of Regions, from 2020, I proposed the methods of reconstruction of physical activity of past human populations. The subjects of my study were two migration periods in 5th, 6th century AD Lombard Germanic Germanic people, populations from Gan and Shamorin, southwestern Slovakia, and their enthesopathies. Those are muscle insertion sites on your bones, on human bones. Since the analysis of the material culture did not provide information about possible repetitive physical activities, as the graves were robbed, it was decided to utilize historical and 3D maps, optical satellite, and LiDAR imagery to analyze the regions inhabited by these two populations. Satellite and LiDAR imagery appear to be much useful compared with historical maps, as these maps are no older than several centuries, while the history of the macro relief extends to the geological history. Optical satellite imagery was analyzed in its different seasons. I also tried to use synthetic aperture radar data, but the swath suite of Sentinel-1 interferometric widebeam is too big for my studied areas. For the first time in scientific research, the synthesis of analysis of statistically prevailing enthesopathies and aerospace imagery of regions was used to obtain plausible hypotheses about physical activity of past populations. This approach allowed to reasonably correlate enthesopathies with manual reclamation activity for one population and rowing, net fishing for another. So, as you already noticed, remote sensing archaeology is directed from space to Earth. But space archaeology is the study of human-made items found in space and their preservation as cultural heritage of humanity. It includes launch complexes on Earth, and then we look up to orbital debris, satellites, and objects and structures on other celestial bodies, for example, the Moon and Mars. In the future, space tourism can affect archaeological artifacts. Therefore, the model was suggested for international cooperation based upon Antarctica. A manuscript by scientists at NASA and ESA raised the possibility of preserving Apollo landing sites for future astroarchaeologists.
The International Space Station archaeological project is the first large-scale investigation of a space habitat from an archaeological perspective. The researchers use new methods to study the space station without being able to visit it directly. These methods include using more than 2 decades of photographs stored in Space Agency archives to document life on board the ISS, observing the processes used for handling cargo returned from the ISS, and developing experiments for the crew to perform on the archaeological behalf. In January 2022, the International Space Station Archaeological Project announced that it had initiated the first archaeological documentation in situ material culture in a space habitat, the Assembling Quadrangle Assemblages Research Experiment. NASA astronaut taped 1 meter squares on the walls throughout the space station. Instead of digging these squares to reveal new layers of soil representing different moments in the site's history, ISS crew will photograph them each day to identify how they were being used and how they change over time. We really need archaeology in space because without the past, there is no future. And archaeology is not only for Earthians anymore. Thank you.
Thank you, Oksana. So, you've seen a whole variety of space-linked research, right? I'm the timekeeper as well of the program. Do you have any question? We have like 2 minutes before we go on to the next session. Is there any question that you have about space research, Earth observation, space law, the path to space, or space archaeology? I don't see any raised hands, but of course, if you're staying after, we have a reception, all the researchers are here, so please go to them and ask your question. Then we will now move on. So we've now looked at research and the relevance of space for society. You are still in training, and space is very inspiring and can also be used as a context for education. So in the next session, we will talk precisely about that. We will talk about space and education, and we have some speakers lined up that will talk about how they do research about how space is taught, but also how you can bring these space topics to the classroom. And we even have pupils from a school here in the front row, and they will talk themselves on the space missions that they are launching themselves, right? So this is what this session has in store for you. And I want to call the first speaker, Hans Bekaert, to the podium to talk about. Okay. You brought a mobile planetarium. Super.
Yes, thank you. Good afternoon, everyone. I'm Hans Bekaert. I'm a physics teacher. And actually, since a few years, I'm also a researcher, a PhD student in the research group of Professor Mieke de Kok. We do astronomy and physics education research in collaboration with Professors Wim van Doren, Hans van Winkel, and Hans Stegen. Our research project is called the SLOPE project. And it stands for Studying Learning Opportunities in a Planetarium Environment. So we work together with the planetarium in Brussels, and you know they have a wide variety in programs, but we are especially interested in the educational program. This means in particular the student visits, the visits to the planetarium in Brussels in the context of the astronomy lessons in school, which in Flanders are taught in a geography course. So what we like to investigate is to what extent a planetarium presentation helps students to understand very basic astronomical concepts. And we hope to be able to advise the planetarium, but also advise teachers and develop learning materials. We don't do this only in Belgium. We do this also in collaboration with schools in Italy, Greece, and Germany, and also planetaria and science centers in Italy, Greece, and Germany. I'd like to start with this beautiful picture. Do you know what we see here? Yes. It are star trails. You see star trails, and in the middle you see the star trail of our pole star, Polaris. It's taken with a long duration shutter time of about 12 hours. And here we learn, in fact, that the stars are moving apparently in the sky, just like the sun does. And in fact, this kind of amazing pictures and seeing the sky and the moon and the planets is for many people the first step to their interest for space and universe cosmology. Unfortunately, we see that it seems to be very difficult to really understand what we see on this picture and what's happening in the sky every day. So we have designed a test instrument, kind of questionnaire with 12 questions, 6 questions about the sun, 6 questions about the stars. We call it the apparent motion of sun and stars test. And we have invited students to the planetarium in Brussels, and we did kind of pre-test, post-test setting. Before the planetarium presentation, we did this test, and after the planetarium presentation, we did a test. And we indeed learned that for many students, it is difficult to describe and explain the apparent motion of sun and stars. We asked the students also to explain their answers. And I share just 3 examples with you. Here the student explains that the sun's path in October is smaller than in September, which is correct. But about 35% of the students think that this is also the case for the stars. And 7% of the students use this idea to the opposite way. They say, okay, during the winter, the nights are longer. This means star trails are higher and wider in winter than in summer, which is not correct. And the last example, here the students says, or about 20% of the students think that if you look at the sun's path, that the position of the sunrise and the sunset is the same every day. It doesn't change throughout the year. And here the student writes, okay, the Earth rotation and the Earth revolution does not influence the position of the sunset. So this indicates that indeed, despite instruction in the planetarium, in school, it's very difficult for students to connect what you learn about Earth rotation and Earth revolution with what we see in the sky every day. So we like to improve this, and therefore we designed lesson materials to use in class, where we introduce the celestial sphere as a model, and we designed also a model for the teacher, so he can explain the motions or the rotations in class, and we try to practice this by giving exercises. We have this for the students, they can work with it on their desk, and we hope by making exercises that it helps students to better understand the apparent motion, because we think by using these models, you take the view from space. While you are on Earth, you see what you see in the sky as an observer on Earth, but if you want to understand what is happening, you have to take the view from space, and we hope that this type of models can help. We have also designed a new planetarium presentation. We go with a mobile planetarium to the schools. There is room for about 24 students in this planetarium, and there we also use these models, because a planetarium typically gives you the view from Earth. And we add to the presentation the view from space by using this model and by using pictures to step, in fact, outside the Earth. So we will use our test again to measure if this new approach has impact and can we improve the results. So we hope, we are doing this right now. Maybe some students or some schools are doing it right now in their school. We hope to share our findings. We hope to share our findings with the teachers and with the planetarium staff. We are going to do trainings also, and we hope by doing this that our research triggers the teachers to bring space into the classroom. So thank you very much.
Thank you very much, Hans. And I think there might be even classes who are participating in this project that are present here. So thank you. We'll move on to the next talk by Arjan van der Star. And Arjan is a geography teacher, and he's actually taken part in analog Earth-based Mars missions. So I don't think he's going to talk about this now, but tonight we have another session. He will talk about it. Yep. Yes.
Thank you. So, good afternoon everyone. Goedemiddag allemaal. Even kijken of het werkt. Ja. I guess you're all here because of a teacher. That's what I hope. Maybe a great teacher. Everybody's here because of a teacher. But teachers are mostly forgotten in these things, except when you saw the previous session. So what I wanted to do was just to give you a quick, short overview of what I've done in the last 15 years in the teacher training. So what I actually do, my job is to create teachers, to make teachers, geography teachers, which are the best, of course. And actually, it started here. I don't know if anybody knows this, probably not, but it's because it doesn't exist anymore. But this was the Dirk Frimout Center. And when I was teaching in secondary schools, someday I was asked, could you help found this, to start this up? So I worked there for over a year, and actually it was really fun to do Earth Explorer, to train people, and also to actually work on the science part and the media part. But then I got another job, which was at Group T teacher training in Leuven. Group T also doesn't exist. Many things disappear. And one of the first things we did was this poster session, a walk through the cosmos at Group T, which is now an engineer department. And then at the same time, actually, I enrolled in this group, the ESA Forum Space and Education. It was presided by Frank de Winne. I don't know if he has seen these pictures because I took them a bit secretly. And it was the age before the smartphones. So you had to stitch all your pictures together. And this was also under the, let's say, with the help of the Prince Philips Fonds. He is now the king, but in those days, he was still the prince. And the idea was actually to promote space and education. And the first thing we did was make a list of everything there was, all initiatives, all websites, all kind of groups. And then actually out of that, a little bit the same, at the same time, grew the ESERO. The ESERO is the, let's say, the educational bureau of ESA. And actually, and what they are doing is a great job, of course. It started in the planetarium in Brussels, but now it's in the, actually Leuven based, so Katrien is now the coordinator. And what I did there, I don't know if you understand, but science of wetenschap en wiskunde technologie, which is STEM at the moment, maybe even STEAM. For me, that's geography. For most people, geography probably is very boring. For me, it's really STEAM or STEM. It's an interdisciplinary science. Most people say it's not a science, but it is. And so for me, that's actually a good starting point in schools to do something about space. So one of the first things I did, I actually don't know why I started with Mars, but Mars is just because I'm actually trained as a geologist, and there's only one thing you can do on Mars, and that's geology. There is no plans or whatever. Probably not. So one of the first things I did with students was to create a workshop on Mars, and this is what I did for many years. The pictures you see are in the Wijnpers in Leuven. I don't know if there are teachers here from the Wijnpers. It is now the teachers' room, but in those days it was their library, and we could use that for a whole workshop. We also presented it in Ostende, the Astro event, which was very large. We even built, well, this was based on a Volkswagen chassis, and so the base of a Volkswagen. We built our own Mars car. And yeah, I didn't put the picture on it, but we used the car because it had to stay indoors at night. We used it to go to the bar, or the students did. And then I actually got the chance to do one specific, very strange thing, is to do a Martian simulation in the desert in Utah. But I'm going to talk about that later in the evening. And this was also a little bit under the guidance of Frank de Winne, who was then who ended the mission, the second mission, and we were able to talk to him on the satellite phone out of the desert, which was quite fun. But you can also see in the picture on the right low-hand side, it was a muddy desert because we actually went there during a snowstorm. So, and then we did a lot of things, a little bit more with the Mars workshop, but then I stopped it actually, and I wanted to do something else. This is a visit at the European Astronaut Center. So I started with Dirk Friemout and Frank de Winne, and this was, I think, the first time that I met both of them at the same time. And actually also, this is a bit, I did a lot of things that I stopped because then I started working for another university college, so which is now UCLL in Leuven. I call it a little bit a disturbance in the force because a lot of things were suddenly not so much possible anymore. But one of the things that I now let my students do is to go visit observatories. So in Belgium. So what they do is they go in separate groups to visit several observatories, including the planetarium. I'm not going to tell you the results, but what they have to do is to perform sort of an audit, and they have to say what they think about it. So the result is in red or green or orange. So the results are kept secret. But that's one of the things that they do. They also did some STEM projects, for instance, about meteorite craters. All based in let's say, in courses that I give. Astro apps, so this guy actually, Vincent Vos, he made a nice website where he tested 10 different apps to be used in the classroom. And this is something that I do with students now every year to go to the Kesselberg, and I pretend to go to Mars. It's a Mars expedition, actually. But it also helps you to think about sustainability, because that's another course that I teach for the international students. And then one of the last things, I see that the text is not there, but this is, we're still working on this. It's like a game concerning space law. You just heard Philippe de Man talk about space law, and that's really something very important at the moment. And I also go to Astropolis. I don't know if anybody has heard of this, but I can really recommend this also because he's a friend of mine. But this is really an interesting science center. It's just like Technopolis, but then especially for space topics. But it's in Ostende, so that's a bit far away maybe. So the previous year, of this year actually, we also worked on the Big Bang City Festival about Georges Lemaitre, but then we created a few teacher materials for well, the first one was about space farming, and the other one was about light pollution. And we also did some experiments ourselves. And then this was an interesting project for schools with, how do you call them, students with special needs. We made videos. Well, Frank de Winne made a video that he made a video call, and Friemout, he was kind enough to receive us at home. And there were 3 schools in Leuven. We had 3 prizes. There was a quiz. So every school would win 1 prize. And the children had to make drawings about the solar system and or aliens, which was fun. The last things I did, so this is a group of students who said, yeah, we want to work with you on exobiology. So this is a teaching package about exobiology. And the idea is actually to think a little bit wider than the constraints of biology and to be more creative, because if you are more creative, you can fantasize about all kinds of creatures, and if you can fantasize about that, you can also start creating technology to measure or to find those creatures. And that's a bit the idea. And then the last thing we did this year was the space meeting. That was actually Oksana. So we just had a meeting with many of the people that are here in the room, were there as well, which was fun. We also had space food. That's always good. And this is another one that I did a few weeks ago. So we actually extracted extraterrestrial dust from, how you call it, mud that we collected from sewer systems or roof systems. It's all for fun, of course. And then we also went to the Space Expo and got to meet an astronaut. So actually today, this is my 4th or 5th astronaut this year. I'm doing well. But I can really recommend this expo if you haven't seen it yet. And actually there I met one of my colleagues of another university college, and I thought I was the only one doing this stuff, but she is also working a little bit on space, and that's I think that's quite important. So these are the courses that I give. It's not to make advertisement or anything, but it's just to show you. I actually get criticized a lot because they tell me, you're doing your hobby. But my job is my hobby. That's indeed the case, and my hobby is my job. Why not? Let's make it fun. It's just what I heard from Ms. Fisher. Mrs. Fisher, Ms. Fisher. And what is important, of what I did actually the previous year was to have a look at how are the things doing with that list that we created of the Forum of Space and Education. And you see that many of those initiatives, website, organizations, they have disappeared. So almost half of them are gone. And the teacher training is still standing, so to speak. So many of these companies, initiatives, they get a lot of money, they do a lot of interesting things, but then it disappears, and which is of course not a good thing, because we want to keep instigating, keep promoting science and space science to young people. So I think teacher training can be another way of promoting that. So now you all want to become teachers, I hope. And the last thing, what I'd like to show you is that actually the last few years, I feel that many students that come to me to follow the education or the teacher training, they often say that space or space topics is the reason to do so. And I'm guessing, I call it the Musk effect. I'm not sure if that's the case. We also have some very nice movies, The Martian, Interstellar, Gravity, and also a book. The author is also coming this evening, but that's actually one of the most popular books on the reading list. They have to read a book every semester. So that's a good thing, actually. There's only one problem within education. We have a lot of problems. So the bar has to go up. Yeah. I don't know if I'm allowed to say this, but I can just say it. So a lot of teachers, and especially in the geography department, it's a problem. 66% of the geography teachers does not have a geography diploma. So you can say, is that a bad thing? Well, of course, I would say yes. And because you may be passionate, but you don't know what you're talking about. So, and the other difficulty is you have a lot of administration. Many of the teachers that are here, please stay in the education. But many of the young people, they stop too early, too soon. And these are the numbers by, I think, 2040. We need 3,200 teachers in secondary education by 2040. That's a lot. I only have 35 this year. And probably half of them will remain by the end of the... I don't know. I don't know how the exams will go, but this is what we need. So people in space industry, people in science, but also people in the teaching business, don't forget this, this side of the story. Thanks.
Thank you very much. Thank you. Thank you, Ariane. You gave a great inspiration, I think, both for the pupils and the teachers here. If you want to have space in the classroom, you saw some great examples. And we're going to give some more examples now, because I would like to call Oriel to the stage, who is going to pitch what she does with exoplanets. Thank you.
Hi, I'm Oriel Marshall. I'm one of the PhD students of Catherine, and I work within the Chameleon Exoplanet Research Network. This is a network of PhD students that is modelling and researching the atmospheres of exoplanets and protoplanetary disks. And so my role within this network is developing... is the microphone working okay? No, it's not. I don't know what to do about that. Just talk louder, I guess. This one? No? Yes? This one? This one? This one? Oh, this one. I see. Okay. There we go. That's better. Yeah. So I work within the Chameleon Research Network, which is looking at the atmospheres of exoplanets and protoplanetary disks. And so my role within this network is developing educational materials based on these topics. So the topics I've chosen in particular is lightning on exoplanets and clouds on exoplanets. So links very well in with the geography that was mentioned previously. And so the route I've chosen to take for this is looking at the differential effect of using space as a context and a tool to teach STEM curriculum subjects in schools. So the way that I'm going about this is I've developed 4 different lessons. 2 of those are about lightning and 2 of those are about clouds. And so I've made a control version, which is just based on Earth, and then an experiment version that's using space and exoplanets. And I hope to teach these in schools and then compare the 2 and find out how effective it is using space as a context for teaching these subjects, which I've got high hopes about. So the lessons themselves are inquiry lessons. So they involve a lot of hands-on experiments. So you can see here the diagram of the little clouds in a jar there. That's something, I didn't bring the jar in with me because it's too big, but it's just making a cloud in a jar using these very simple steps, just with like hot water and hairspray. And then I've got with me here the materials that's needed for the lightning experiment. So as you can see, all the materials are pretty affordable and accessible, which I think is really useful for having them in the classroom. And so if there are any teachers who are interested in getting the teacher trainings for these lessons, they'll be run over the next semester and hopefully beginning next semester. So there's either a QR code in there you can scan, or you can come and find me or email me, and I'd be very happy to talk more about it. Thank you.
Thank you, Oriel. And we've managed to fix the mic. So, yes. The next slide. Yes. Okay. Peter.
Hello, I was given a full minute, so wake up your neighbor. It's going to be interactive. Raise your hand if you know what STEM is. Keep your hand raised if you have been actively engaged in a STEM project or teaching a STEM project. And who is known with STEAM or has engaged in a STEAM project? That is a lot less. So the A in STEAM stands for art. Yeah, you can lower your hand. Great. Find me after the session. The A stands for art, and I am an artist. So my name is Peter. I'm a colleague of Oriel. I work with scientists, exoplanetary scientists, specifically to find out whether we can use art and artistic methodologies to further scientific research, specifically scientific ideation. So not only for dissemination, we know that works, we need artists to bring forth visuals and graphics to the public audience, but we also think that we can use artistic methodologies to further research. Find me after the session if you're involved, if you want to be involved in this, if you have ideas about this, or reach out through email, or come later tonight at a session at 8 here in Leuven, where I'll be presenting one of our projects. Thank you very much.
Thank you, Peter, for this very concise STEAM talk. Now we'd like to ask to the stage the pupils of the St. Peter's College in Jette, and with their teacher, Erik de Schrijver, who is really a space teacher, space ambassador teacher. The floor is yours.
Thank you, Professor Kohlenberg. Thank you for inviting us. It's a real honor and a pleasure to be here. My name is Erik de Schrijver. I've been a physics and chemistry teacher at St. Peter's College Jette, Brussels for many years now. I do have the required degree to teach physics. What I'm here for is that I hope to show you that space is not a frontier. The sky is not a frontier, even not if you're only in high school. So in the fourth year at our school, the students within the curriculum of STEM have built a clinostat over the past few weeks. They have been assembling the mechanical parts, the electronics. They are now in the process of refining the software Arduino code that is driving the stepper motor. So very soon they will be ready to start investigating plant growth under simulated but adjustable gravity levels. The plan calls later this year to build a full random positioning machine to simulate zero or lunar or Martian gravities.
Hello, my name is Alexandra and I'm in the 5th year of Modern Languages Science. I will be working on a muon detector. This is an internet project by MIT in the US that uses a plastic scintillator and a silicon photomultiplier to count muons. We hope to fly our detector on an Asgard weather balloon in March and be able to construct an altitude profile for muons in the atmosphere from sea level up to about 30 kilometers, which is deep in the stratosphere.
Hello, I study science mathematics, and my name is Robin. Neutron counters can be either based on helium-3 or boron-10. In both cases, a neutron capture event results in a charged particle being created, an alpha for the boron-10 reaction. And this alpha particle can be used to start an avalanche breakdown in a Geiger counter-like setup. We purchased a Soviet-era boron line tube from a supplier in the Ukraine, and we will be designing and building the necessary circuitry as our contribution to the Asgard balloon flight on March 2023. as there is hardly any detailed info to be found on the internet for this. It's more of a challenge than the muon detector of our esteemed colleagues.
Good afternoon, I'm Tristan. I'm in my last year science mathematics, and I participated in the recent European Hemera balloon campaign for high altitude research. Our team built a set of instruments called strains. Strains included Geiger counters, solid state detectors, a filter wheel to study the effect of thin metal shielding on radiation, makes things worse, and gamma spectrometers using scintillation crystals to obtain an energy spectrum of hard X and soft gamma rays at various altitudes. The flight took place early September in Arctic Sweden, and data processing is now underway at our school.
Good afternoon. My name is Camilla Bouzamour. I'm a fifth-year student studying human sciences. Unconventional indeed, but I believe it takes all. On a serious note, I'm working on IGIS-2, which is a solid-state radiation detector that will be flying on a sounding rocket in April of 2023. The rocket will not reach orbit, but it will go into a suborbital flight that will reach well above the Kármán line at 100 kilometers. The Kármán line is generally known or accepted as the boundary of space, which makes it kind of interesting. The challenge of this experiment is the startup circuit that will detect the launch. As we have no information or no signal from the launch control, and sometimes they get postponed or delayed. Therefore, our experiment needs to be powered down, or our battery list will deplete and exhaust, which is also not pretty. Point is, when the launch occurs, it needs to start detecting it as fast as possible, since the rocket will go from 0 to Mach 6 in less than a minute. Thank you.
So, good afternoon. My name is Kathy, and I'm in my last year of latent sciences. And we've been also working on a project called Paragarnus, an experiment we were thrilled to see selected for the first flight of ESA's new launcher, Ariane 6. And what Paragarnus is supposed to do is to measure the Earth's magnetic field and to measure the hard X and soft gamma radiation level in low Earth orbit at 580 kilometers. And as part of ESA's debris mitigation policy, it will not remain in orbit, but be brought down to burn up in the atmosphere approximately 10,000 seconds after launch. And we have also asked 2 other schools to help us share the workload. So Celico Emmanuel Dilson will be working on the iridium communication system, and Institut Valais-Bailly has designed our startup circuit. So.
Now, obviously, these are not projects that you can hope to bring to a good end as a beginner. But then again, when we started out way back in 2004, we did passive biology experiments. We flew plant seeds, we flew eggs of brine shrimp on weather balloons flown by an amateur group in the United States, actually. And over the years, we painstakingly worked our way up, constantly on the lookout for flight opportunities. And that is something I'm glad to say that you won't need to worry about, as we now have the Asgard balloon program for secondary schools worldwide. It's an international program where high school students get the chance to fly their experiment, their idea, on a balloon to the edge of space, and you get the chance to socialize with, to communicate with, and to befriend like-minded students interested in space and space exploration worldwide. You can see the number of countries here that have participated in the past. So if you want to start a space program at your school, you can do that now. You can apply for participation in the Asgard 12 balloon mission that will fly from Brussels in March of 2023. Deadline for submission of proposals is November 11th, so you still have time. Don't lose it. Start thinking about the project and submit your proposals. Thank you.
This is quite impressive, isn't it? Very impressive work. So, thank you very much. That brings us to the end of this session. And I represent ESERO Belgium. ESERO is a European Space Education Resource Office, which is the school program of ESA. So if you want to do something in school linked to space, come talk to me or to Peter. Peter is there. And Peter, you have a stand set up there as well, I think. So during the reception, you can get more information about what ESERO does. But basically, we make lesson materials, we offer teacher trainings, and we also promote special projects like the one that Erik started, Asgard, as well as projects about building your own moon base, launching your own small satellite, or writing code to be played on the ISS. So if you want to know more about this, just come and talk to us. Then some of you are planning maybe to work in space in the future. So there's a lot that you can do here at KU Leuven to become involved in space. And here is just some of the master programs that are mentioned here. There is a stand also in the reception hall, which is just across from this room, where you can get more information on each of these programs. Okay, and that brings me to the end of this session. I think we should thank all the prominent people again. The astronauts, they have had a very tiring week. They arrived last weekend, and since then they've been touring the country from early morning till late at night. I think, Anna, yesterday you only returned at midnight, and then in the morning she was back again here. So really, all our appreciation for what you have done to inspire people in Belgium today, this week. And I would like to now give the word to our Dean of the Faculty of Sciences, Philippe Muchet, who will speak the final words of the session.
Thank you very much, Katrien. Well, it's a real honor, a real pleasure to be here for the closing words. It was a fantastic afternoon. I think, I'm sure that you learned more in these 2 hours than you could learn sitting at a bench with all these people here. And what I really learned today is, and this is really the key of science, of STEM, of all what we are doing, is from the astronauts, from the professors, from the researchers, from the colleagues from the schools, from the students, one thing they all had in common was enthusiasm, was inspiration, and was hardworking, and really taking their future in their hands. And I think that's really the main message. The other thing I learned today also is we came here for a space day, and already from Frank and Anna, what was intriguing was really that they were coming from space, but really looked also down to Earth, looked to humanities and how we should go on with our Earth, with the Sustainable Development Goals, with boundaries, and how we should be open-minded always when we look at other ideas and other positions people take. So indeed, that was really fantastic. I'm not going to talk about the education because I'm dean and responsible for education, but there is a stand and you can go to it and learn more about all the possibilities at this university or other universities here in Flanders, in Belgium and in Europe. And there was already reference to Delft also today. I also would like to say a few words about that. We are also still appreciated what is going on because I learned this week that Thomas Hertog, who was one of the key persons in organizing the Knal Festival, won a prize, and also Jan got the prize for communication outreach. And indeed, the Faculty of Science has heavily involved in organizing the Knal City Festival with focusing on the Big Bang. We had the pleasure to organize Katrien, Cleo, Connie Aerts, the fantastic days in March. We were also glad to have Frank de Winne and Dirk Friemout here for talking to and contributing to these days. And today, it's fantastic to have these Space Days. Also, another colleague we're really proud of is Connie Aerts, is actually an astronomer and won the very prestigious Kavli Prize, which is comparable to the Nobel Prize, and we hope also that later on she will win the Nobel Prize. We just have to wait for it. But I think it's really time now to thank all speakers, these really extremely enthusiastic people. They continue talking about years about what they learned and what they achieved in their life. And also the young people already are contributing to this day. So a warm applause for all contributors today. A warm applause for these very enthusiastic people. Last but not least, a warm thank and again a warm applause for the organizers of this day. Katrien, who's really leading in the whole group. And I'm sure everyone in the room is looking for more. But now I have the pleasure to invite you for the reception which takes place in the room opposite of the corridor here. Have a nice weekend.